All right, everybody. I think I'll go ahead and get started here. Welcome to Thursday, and boy, it's chilly outside. I got up really early this morning, and it was so foggy and cold. Not used to that. Not as cold as the top of the mountains in Ecuador, though. I'll tell you that much. Um, let's see. I do want to make a few announcements here. The reason I got up early this morning was so that I could bring my car right up to the loading zone and take a bunch of stuff from my office and put it in the car. Why was I doing that? Well, because I found out a day or two ago that they're going to close the room that is outside of my office starting at 4 o'clock today because they're going to put new furniture in. It's going to be really nice. They're going to have like places for students to write on the tables and stuff like that. It's going to be a really neat deal, but they picked terrible timing to do this because it's right at the end of the semester. And so, what I wanted to let you guys know is that my office hours later today. So, I am going to go down to have office hours right after class as well. But my office hours today are going to be in here. I'm just going to stay in this room this evening. I usually have evening office hours, as you know. Of course, I'll have Zoom as well, like always. But so my office hours today, right after class from 12 to 12:30, like I usually do. But then starting from 5:30 until 10, there's an hour and a half that I take a dinner break, of course, as you know. But these office hours here will be in this room. I am just going to stay in here because they are closing down that room outside of my office, and I don't even know if I'll be. Nobody told me. They haven't even told me if I'll even be able to get into my office. That's why I took a bunch of my stuff and put it into into my car this morning. Um, Supposedly they're going to be done with that by tomorrow afternoon. I really hope that they will. Um, I'm also going to have some extra office hours because of our exam coming up. So on Sunday, as you guys know, I normally have office hours in the evening. I'm going to add a little bit more to it than that. I'm going to have, so you might want to write these down because I don't think I've written them down anywhere else yet. From 1 to 3 in the afternoon, and again from 8 o'clock onward. And those hours I hope will be back in my regular office. If for some reason we can't get into that room, I will email you guys and tell you where I'm going to be. So that's on Sunday. And then on Monday, I'm going to have extra office hours from 1 until 4 p.m. And then again, starting at 9 p.m. in the evening. So these are Sunday and Monday office hours. Our exam is on Tuesday, right? So I'm going to try to be around a lot of extra times on Sundays and on Monday this week. And then also don't forget that I've decided to do a review set, well, basically 2 versions of the review session. So I'm going to just hang out all weekend pretty much around Fullerton. So what are the review sessions? I'm going to do one of them on Sunday from 4 to 6 p.m. And this will be in this room. And then I'm going to redo it, or basically, I might have a few new things to say on Monday. But on Monday, I'm going to come in from 7 to 9 p.m. Okay. I will be recording the review sessions and I will send out a link with video for you to watch if you don't want to come in, but you'd like to see the review. This is totally optional and nobody has to do this. There's already a recorded review session in the resources folder. So it's not like you don't have anything else to look at. This is just a extra thing because I was gone for so long. I felt like I should try to be really, really available this weekend. So yeah, grab a photo of that if you need to, of what my hours are going to be. The other thing I've decided to do is we only have 2 homework assignments left. And one of them is before the midterm, which is number 23. I was originally going to make it due tomorrow night. It would still be better if you could try to finish it by today or tomorrow, but I'm not going to actually make this due until Sunday night. That way, just in case people can't get a hold of me today and tomorrow so easily, on Sunday, of course, I will be around a lot and I can help you with this assignment. Okay. So, your next homework assignment is not due until Sunday, and it will be based on the stuff we covered on Tuesday as well as what we're going to do today. Both of those things. Okay, so that's kind of where we're at with that. And then everybody knows, I think, that the exam is on Tuesday. So the exam, I talked a lot about that on our last class, as sort of what it covers, and I went through the review packet, the review materials in the resources folder. So I think that's all kind of up there and set up for everybody. Does anybody have any questions about any of this? I'm basically going to try to be really around on Sunday and Monday, pretty much all afternoon and evening, both days. You can more or less count on that. I'm assuming that the office space will be open again. Again, anybody looking for me this afternoon should just look for me here. Because I think that the office space outside my office is going to get closed down for a little while. Okay, so that's all I got for announcements, I think. Everybody clear on all that? Yeah, I've had people outside my office already studying for the exam. It's been great to see. People are getting ready already, so I encourage you to start thinking about the exam as soon as you can. One last thing, I checked my SOQ response rate this morning because I'm going to give extra credit to everybody in this class. 3 points towards your final exam, assuming that I get 90% SOQ response rate. It is still hovering around 67% or something. I need about 8 more people who have not done an SOQ to do it, and you have to do it by tomorrow. Tomorrow's the last day to do it. So I would really appreciate that if you could fill out an SOQ form for me. And I imagine that your classmates will appreciate it too. So anyway, that is it for my announcements, I think. Yeah, so so those are the answers to all the test questions. Just kidding. He's not listening. Anyway, let's see. Yeah, so let me take a few minutes and recap what we did on Tuesday. If you just came in the room, Marco, you might want to grab a picture of what's on the board there. We are still trying to solve linear systems of differential equations. Okay, so this is actually the same exact recap that I started with on Tuesday. Here's our linear system. Okay, n is a number that's usually 2 or 3 for most problems that you're going to do by hand. And remember that the solutions to this system, right, they form a vector space. And the dimension of that vector space is n. Okay? So the size of the matrix is going to tell you what n is, and that's going to tell you the dimension of your solution set. In turn, that tells you how many basis vectors you have to have in order to span the solutions, right? So that would be n, whatever it is. And we talked on Tuesday about our strategy for finding those solutions, right? The idea was that we could just look for eigenvalue, eigenvector pairs for A. This is really nice. We learned how to do this in chapter 7. So we find these eigenpairs, and then we can just form solutions that kind of look like this, right? E to the lambda t times v. That's going to be the idea, all right? And if we find n of those, if we can find n eigenpairs like this, then we can build the sort of the general solution. This is what I'm writing here, x of t, as a linear combination of all of those solutions that we find along the way, right? And this assumes that we can get n of them, right? So this would mean we have to have n eigenpairs, right? N eigenpairs. So, but if we can get that, if we can get n eigenpairs, we're good to go. We can write down the general solution to our linear system. Okay. Now, I mentioned there's a couple of hiccups with this that we have to be careful about. One of them is that it's possible, as we learned in chapter 7, right? It is possible that the eigenvalues or eigenvectors could be complex numbers, right? So I put a little note down here. We talked about this last time. If we had, say, a plus or minus bi as a complex pair of eigenvalues, and then the corresponding eigenvectors would also have kind of a real and a complex part, so I'm writing that as R plus or minus SI, then, the way we would write the solution here would be, e to the lambda t times v, right? It's exactly the same notation that we have in the box here. But the problem is we don't like this as an answer because it has I in it. It's not a real valued solution. What we would like to do is extract two real solutions from these two eigenvalues, which are complex conjugate pairs, right? And the trick to doing that, which we learned on Tuesday, is to sort of go through the motions of using Euler's formula. So e to the bit can be rewritten using Euler's formula as cosine of bt plus I times sine of bt. That's my, e to the bit. I still have e to the at out in front. And then my vector is still here. And the trick is to FLOY it out, as we talked about. It's kind of a FOIL process. You have something plus something times something plus something, and you can FOIL that out, but you do it in the order of FLOY. So if you put the first and the last together, and then if you put the outers and inners together, you can make these two real valued solutions. So I just wanted to remind you about that. When you have complex numbers showing up as the roots of this auxiliary equation, then, as the eigenvalues of the matrix A, if you have those complex numbers, then you're going to have to do this process. I have some students who will ask me, is it okay if we just memorize where the cosine and the R and the S and the sine go, like what matches up with what? You could actually figure that out if you wanted to. I don't think it's worth memorizing it. I think it's better to just FLOY it out every single time. And that way you don't have to learn something extra. You can just take an expression like this and just do firsts and lasts to make one solution, and then outers and inners to make another solution. And you don't have to memorize anything. So it is true you could memorize it, and some students like to do that, but I personally would rather just kind of go through the motions each time. Are people following me on this? Is this all clear enough? Any questions that's left over from just kind of reviewing what we did on Tuesday to make sure everybody's comfortable with where we're at here? Right. So one hiccup with this whole strategy is that we could get complex numbers for the eigenvalues and eigenvectors, and that we have already addressed. We addressed that by using this FLOY approach. Okay, but I said that there were a couple of hiccups, and the other hiccup that we can run into we have not addressed yet, and that is, what if we don't get n linearly independent eigenvectors? In other words, what if our matrix A is actually defective? Some eigenvalue doesn't pull its weight, and we don't get n terms here, right? The solutions are supposed to be an n-dimensional vector space. I have to have n solutions if I expect to really have the general solution correct, right? So I have to get n solutions. There's no way around that. But the problem is that if the matrix is defective, we won't get n eigenpairs to make n terms of our general solution here, and we're left sort of hanging. What are we going to do about that? So that's what we're going to address today. Before I do that, though, I just also want to remind you, I put this on the sideboard so I wouldn't have to erase it too much. Don't forget we talked about phase portraits for 2x2 systems only. So this is if n is equal to 2. I'm not going to go over all of this again right now, but you should learn these 6 different scenarios, right? Notice that all that matters, all that affects this qualitative phase portrait is the eigenvalues. So even without doing any of the eigenvectors, if you just know the eigenvalues, are they positive? Are they both positive? Are they both negative? Is there one of each? Are they complex numbers, right? You can decide just based on that, which of these 6 qualitative pictures would represent what's called the phase portrait for the system. Okay, so I talked a little bit about that and showed you some examples on Tuesday as well. So I just wanted to remind you about that, that is also something I want you guys to be aware of. Okay? All right. So any questions so far, guys? Okay. Does everybody have all this stuff down? Take a picture of it if you need to. Maybe I'll try to save it for a couple more minutes in case somebody else comes in. That's just all of my office hours for these next few days as we get ready for the exam coming up. But I would like to address that second hiccup now. Okay, the first hiccup we're already done with. If we get complex numbers, we're going to use Floyd. Okay, but the second hiccup is what do we do? And this is the next section. And this will be on the exam on Tuesday, which is 9.5, is what if A is defective? What if the matrix is defective? What if we don't get n linearly independent eigenvectors to make these eigenpairs and these solutions out of? What are we going to do? Okay, so that's what we're going to talk about here, the first half of our class today. I'm going to give you, show you an example of this to kind of get us warmed up on this for today. So an example might be something like this. Solve x prime equals a times x, where A is going to be this matrix right here, a 0, -2, and then the second row is 2 and 4. So it's just a 2 by 2 matrix for this one to start off with. And I'd like to tell you guys that I am only going to cover this topic for 2 by 2 or 3 by 3 matrices. It's not that you can't look at larger matrices, but if the matrix was 4 by 4 or larger, you really should use a computer to do this. It's just too computationally technical. So you'll get the idea of what's going on just with these matrices here. So I will not give you a matrix that's larger than 3 by 3 in this section, okay? Which actually has a nice side effect. If the matrix is not larger than 3 by 3, then you can be guaranteed that there will be no complex numbers in this section. And that's because if the matrix was defective, remember, in order for a matrix to be defective, the eigenvalues have to repeat, right? Well, if you had, you know, A plus BI repeating, right, at least 2 times, well, you also have to have the conjugate. Remember, they always come in pairs. So how many lambdas would you have to have in order to have repeated complex conjugate pairs? Well, the answer is you'd have to have at least 4. And you don't get 4 eigenvalues if your matrix is only 2 by 2 or 3 by 3. So in this section, you will not see today any complex numbers. Yeah, Audrey?
I was wondering, like,
so the number of lambdas that a matrix has, including all repeats and all complex numbers, it is always n. It is always n. So if the size of the matrix is n, I had a few people on that extra credit quiz. It was I think it was a 3 by 3 matrix, and I had some people giving me 4 lambdas. And so I had to like cross that off, right? It has to be exactly n lambda values. Okay, and that's because the characteristic equation for the matrix will be a equation which is a polynomial of degree n. And one of the important facts about polynomials of degree n is they have n roots. Including repeats and including complex numbers, there will be n roots. Does that answer your question?
yes.
Perfect. Okay. So for example, here, I know that this matrix will have 2 lambdas. In fact, let's go ahead and start working this out. Let's see if we can find them. I'm going to do the determinant. The first thing to do to find the lambdas is to work on the determinant of A minus lambda I. So I'm going to subtract lambda off of the main diagonal of this matrix. Okay, so the first step is to get the eigenvalues. So here we have a 2 by 2 determinant. So I think we all know how to find this determinant. We take AD minus BC. So in this case, negative lambda times 4 minus lambda, and then plus 4. And if I just multiply this out, I don't mind multiplying it out. It's only going to be a quadratic. This will give me lambda squared minus 4 lambda plus 4. And that can be factored actually very nicely. It's just lambda minus 2 quantity squared. Okay, and of course, as always, we're going to be setting that one equal to 0. Okay, we're going to set that equal to 0. And so what are my lambda values? 2 and 2, right? Same lambda shows up twice. Does that automatically mean that the matrix is defective?
No.
Not necessarily. Not necessarily. We have a little bit of a concern whether this will pull its weight or not. So it's a maybe at this point. If we want to know, is this matrix really defective, we now have to consider the null space that goes with that eigenvalue. So we're going to take lambda equals 2, and we're going to do a null space here, guys. Okay, so how does that work again? Well, we just subtract 2 from the main diagonal of A. So I'm going to go ahead and subtract 2. So that's going to give me -2 and -2, and then 2 and 2. As always, this matrix should be not invertible because we were setting the determinant equal to 0 in deriving it. So this is a non-invertible matrix. You have to be able to cross off a row. I'm just going to go ahead and cross off the first row. And now I'm going to use my, well, first of all, I'm going to actually cut this second row in half. I'm going to make it a 1 and a 1. That's just multiplying the second row by a half. And then I'm going to create my eigenvector by using the AB trick. So I'm going to forego the free variables that we so often use and just go ahead and use that trick that you've seen me using these last couple of weeks quite a bit. Okay, so there you go. And now do we know if the matrix is defective?
Yeah.
It sure is. It sure is. The eigenvalue has a weight of 2. A multiplicity, in other words, of 2, and yet only produced one eigenvector, right? So that means that this eigenvalue did not pull its weight, and so this is defective. Now, we can still make one solution to our system here, because we do have one eigenpair, right? We do have at least one. So let's go ahead and milk it for all we can. This is just going to be, right, e to the 2t times -1, 1. I'm going to go ahead and put a box around that so we can find it later. But we at least get one solution pretty easily, okay? But the problem is how to get the second solution. You guys, remember, x2 of t, right? We need to find that. Remember that n is 2 here. In this problem, it is a 2 by 2 matrix. And so my solutions should be 2-dimensional, which means I need 2 of them. I need 2 solutions in order to build the general solution. And right now, I only have one. I only have one so far. The question is, how do we get the second one? Well, it's the same answer you've heard me give many times before, which is that somebody way smarter than me and way before I ever came along managed to guess what was going to be the right solution. Now, one common and popular mistake that I see people do here is they say, oh, the eigenvalue was repeated, so don't we just stack x's? You might remember in the last chapter when we would have repeated roots of an auxiliary equation, what we did to sort of create additional solutions when we had repeats was we stacked x's, okay? And so people, sometimes I will see students trying to do that here as well. And the first thing wrong with it is that you wouldn't be stacking x's here, you would be stacking t's, because the variable of these functions is t, not x. And the second point is that actually it just isn't the right thing to do. Turns out that the way to get additional solutions is not to just stack t's like we were doing before. So what we're going to do is we are going to guess a trial solution. So how is it going to look? Here it is. I'm going to put it over here. Can everybody see this over here? Yeah, because this is very important. I'll put it in a box in a second. So you create the second solution by using the e to the lambda t again. And then instead of putting v here, what we have to do instead is a little more complicated, which is we're going to put W1 plus T times W2. Okay, so let's put a box around this because this turns out to be really important. The form of the second solution is going to be the same e to the lambda t that we have already used before, but now the vector here is not just an eigenvector. It's not just v. It's not just the v that we wrote down right here. Okay, instead, we have to play a little bit more of a tricky game and put W1 plus TW2 here. And I'm just going to say where W1 and W2 are to be determined. To be determined. That's going to be the secret. Wow, somebody came in here overnight and made this board a lot nicer today. Very happy about this. After racing on Tuesday, I didn't even have to go to the gym. My arms were already, I'd already had a pretty good workout. So, yeah. I say where W1 and W2 are to be determined. How are we going to determine them? By the way, this is not really in the book. It is in the book. It's just done very generally in the book. And so I think you're going to like focusing on my notes for this particular discussion. What we're going to do is we're going to take this guess and we're going to plug it into our system over there, right? X prime equals AX. We're going to plug it in on the left side. We're going to plug it in on the right side. We're going to match it up, okay? So I'm going to show you how it's going to work. So the left side says take the derivative. Okay, so let's take the derivative of that thing in the box over there, right? So x2 prime of t. Right, we'll go ahead and take the derivative of it. Oh, I see that we're going to have to use the product rule, right? Does everybody see we have e to the lambda t in front, and then we have a w1 plus tw2 in the back. That requires the product rule. So I have to take, how's that work again? The derivative of the first term, that would be lambda e to the lambda t, times the second term, which is w1 plus tw2, and then plus the first term times the derivative of the second term with respect to t. The derivative of w1 plus tw2 would just be w2, right, if you're differentiating with respect to t. So that's the derivative of our trial solution. Okay. But then we need to set that equal. We need to set that equal to what the right-hand side would be, which is a times x2. And x2, again, let's just, we don't need a parentheses here. Let's just write e to the lambda t times w1 plus tw2. There you go. So I'm going to go through this derivation and then we'll get to a nice summary. You won't have to remember this derivation. Okay, I'll tell you when we get to the punchline. I'd like to simplify all of this. Does everybody notice that there's an e to the lambda t in every single term on every side of the equation? We can just cancel all of those, kind of get that out of our way. And then what I notice now is that some of the terms on both sides of the equation do have a t with them, and some of the terms do not have a t with them. And what I can do is kind of balance them out, right? Anything with a t on the left should balance anything with a t on the right. And anything that doesn't have a t on the left should balance anything that doesn't have a t on the right. So what I'm saying, guys, is let's look at the t terms, and then let's look at the non-t terms. I'm going to kind of group the terms into two parts. So I am going to underline in blue the terms that have a t with them. Here's a t right here. I'm going to underline that, but as I do that, I also have to remember there's still a lambda here in front. So don't lose track of that. That lambda is being multiplied by T W2. So that's a lambda W2 right there, right? On the left side. And what is the T part on the right side? There's an A and a TW2, exactly. So if I just say, well, what's the T part on the right side? It's AW2. Look okay? I'm just doing the algebra. I'm just kind of matching it up. Here's it. I'm ignoring the W1 pieces right now. I'm just looking at the parts where there's a T. So here's a T on the left, and here's a T on the right, and the things that are multiplying that T have to match up, right? If I tell you that AT plus B is equal to CT plus D, you guys would all agree with me, I'm sure, that A has to equal C and B has to equal D. That's all I'm doing. I'm just literally matching terms up like that. Okay, so what about the non-T terms? The terms that don't have any T's in them. Let me put some red highlighting on this part. Here's a W1, right? And it still has that lambda there. So lambda W1 on the left. But also there's W2 right here, right? So I'm going to add W2 as well. That does not have, underline that as well, that does not have a T on it. And then on the right side, where are the non-T terms? Well, I have the A times W1. A, W1. Look okay? All right, now guys, I am going to rewrite these a little bit. By the way, does this look familiar? I see people nodding. You guys remember the most important equation in chapter 7? The most important equation, I've harped on it so many times, right? AV equals lambda V. This is where all of the stuff about eigenvalues and eigenvectors started. Well, what this blue equation looks like it's telling me is that W2, this W2 that is to be determined, I now know a little bit more about it. It's actually going to be an eigenvector, right? With corresponding eigenvalue lambda, okay? But what I'm actually going to do, guys, is I'm going to subtract everything to one side of the equation and make that into a 0. So just imagine subtracting the lambda to the right side so that I'm left with just 0 over there on the right side. Notice that I have inserted the identity matrix here because it doesn't really make sense to take A minus lambda. That would be a matrix minus a number, which doesn't make sense. So I have to put the identity matrix in there like so. Okay? So W2 is an eigenvector. And what about W1? I'm going to do something similar here with W1. I'm going to do A minus lambda I times W1. I'm going to put all of that together. So I'm going to subtract this lambda W1 to the right side. And I'm not actually getting equals 0 this time. I'm actually getting W2 here. Okay, so I'm just rearranging the equation, guys. I'm not doing anything but algebra to create these two equations. Okay? So, what is the whole goal of what I'm doing right now, by the way? What is this whole whiteboard about over here? The whole thing I'm doing is trying to figure out what are W1 and W2. We've got the form, right? Whatever genius figured this out, that this is going to work, right? So we got the form. It's just, well, what is W1 and what is W2? I now have a little better picture of it. The W1 and the W2 are going to satisfy the blue equation and the red equation. And now I'm going to write down something that, as I said, is not really in the book, but which is, I think, the easiest way to figure out how to do this, which is to draw a little diagram. And here's the way the diagram is going to work. I'm going to start with W1, and I'm going to draw a little arc. And every time I draw one of these arcs, that's going to cue in my mind that I need to multiply by A minus lambda I. So this, I'm just trying to have you understand what my notation or my picture is going to be. if you learn this picture, then you don't have to remember any of the rest of the stuff on this board. So that's why I like the picture. The idea here is that if I multiply W1 by A minus lambda I, what am I supposed to get? W2, right? See, that's the red part, right? A minus lambda I times W1 is supposed to give me W2. Let me put W2 right there. Okay. Now, the thing is that if I start from W2 and I multiply by A minus lambda I again, now what am I supposed to end up getting? 0. So my friends, this black diagram here summarizes everything of the derivation above it. And you don't need to remember anything above. The only thing you really need to remember is this thing right here, which, as I said, is not really in the book. It's not really in the book. So just be aware of that. Now, I still need a little more guidance about how do I actually find W1 and W2. We've already said that W2 is supposed to be an eigenvector. We see that from the blue equation. But, you know, it's actually kind of hard to start from W2 and then go figuring out in reverse what W1 is. It's actually not so easy to do. So you know the best way to do this is to not even worry about W2 at all. But instead, what we are going to do, guys, is we are going to choose W1. And when I say choose it, I mean that there's going to be many right answers. We're going to have a choice about what that is. So now I think I will erase a little bit here. So what are the rules when we choose W1? The rules are that by the time I do A minus lambda I twice, that would be squaring it, right? Every arc, remember, every single arc means I'm going to multiply by A minus lambda I. So what I know here is I have to choose W1 such that A minus lambda I squared times W1 is 0. Right? So that's what this is saying. A minus lambda I squared, if I start at W1 and I hop 2 times to the right, I have to hit 0. Hopping to the right just means multiply by that matrix. Okay, so if I multiply twice by that matrix applied to W1, I have to get 0. However, there is one other important thing, which is that if I only hop once, I don't square the matrix, I only hop once, I'm supposed to land on W2. And W2 is an eigenvector, which is not supposed to be 0. So I'm going to put not 0 here. Because, well, here's the thing. If it was 0, if A minus lambda I times W1 was 0, then you would be basically saying that you want W2 to be 0. If W2 is 0, then when I come back over here to my trial solution, if W2 was 0, that's actually bad. Because if W2 is 0, then what am I left with here? E to the lambda t times W1, and W1 would just be an eigenvector if it's getting killed already on that first hop. You wouldn't be getting a second solution at all. You would just be reproducing your first solution. So you don't want that. You want this, you want W1 to survive 1 power of the matrix, but not 2. Okay? This is it. This is the story. Everybody okay with that? Let's come back to this example now and see if we can finish it. We're supposed to choose W1 and W2 so that specifically W1 needs to survive A minus lambda I, but it should not survive the square of A minus lambda I. So I do have a question. What is A minus, in this case, so let's go back to the example. A minus, the lambda was 2, right? So the lambda value is 2 on this problem. what is A minus 2I? Let's see, it's actually up here. Very important point, guys. When I do the A minus lambda I have to do A minus lambda I, not a row reduced version of it. So here you see I crossed off a row and I cut the second row in half. That was just to help me come up with my eigenvector here, right? But when we're doing this W1 and W2 thing, we need to use the original A minus 2I. So let's be careful with that. It was this matrix right here. So please do not make the mistake of using a ERO reduced version of the matrix. You actually have to use the matrix. So what I need right now, guys, oh, and then let's square that matrix. Let's square that matrix. That means I put the matrix times itself. -2, -2, and 2, 2 times itself. I just want to see what is this going to actually be. If I do my usual dot product matrix multiplication here, I'm going to get 4 minus 4, which is 0. 4 minus 4 is 0. -4 plus 4 is 0. -4 plus 4 is 0. Oh, it's all zeros, as it turns out. I should point out that that will not always happen. We'll see an example a little later today where that doesn't happen. But in some ways, this makes our life easy. Because we're trying to choose W1 so that it won't survive this matrix. Well, the fact of the matter is, nothing would survive this matrix, right? If you put any vector here whatsoever, and you multiply it out, you will get 0, 0, right? There is nothing that is going to survive this matrix, so this part is a slam dunk, right? This is automatically going to be true. You're going to have that no problem. The only thing you really have to be careful with here is you need to choose a W1 that will survive this matrix. Meaning that if I put, so I'm going to try to take a bold step here and do it. Can somebody think of a vector that I could put here, just 2 slots, right? That I could put next to this matrix and it would not turn it into 0, 0. 1 and 0. How about a very easy thing to choose, like 1 and 0? Don't make it extra complicated. Choose something really easy. Now, why is that going to work? Well, if I put 1, 0 right here, and I imagine multiplying it out, you'll actually just pick off that column. And that will be your W2, right? Guys, how do you figure out what W2 is? W2 is just A minus lambda I times whatever your W1 was. So if you chose W1 to be this, then W2, I'll just put it here, would be -2, -2, 2, 2 times 1, 0, and that would be -2 and 2. Now guys, this is not the only correct answer. Marco gave me 1, 0. You could have given me a lot of other things. You could have given me 4, 9 or 12, 6. Or basically anything that does not get killed by this matrix, right? You would like your vector to survive that first matrix. You don't want it to survive the second matrix, but that's a slam dunk. Nothing's going to survive the second matrix, right? So that's it. So then what is my x2 of t, guys? We're actually done. x2 of t, I'm going to put it right here. Here's the form. We now have our w's that we need. E to the 2t. E to the 2t times, what does that say? W1, which we chose to be 1, 0, plus t times W2. What was W2? -2, 2, right? So -2, 2 goes right here. And that, my friends, is your x2 of t. I'm going to put a box around that. Put a box around that one. And then I can go to my general solution now, because I have my two solutions. So what is the general solution? I'm going to write it down over here, I think. General solution is x of t equals C1 times the first solution, which is in the box over there that we got quite a while ago, e to the 2t times negative 1, 1, plus c2 times e to the 2t times, now I've got to put 1, 0 plus t times negative 2, 2. And that would be the answer. Okay? That would be the whole thing. By the way, something that sort of reassures me that I probably did this right is the fact that we made the comment earlier that W2 should have been an eigenvector. Now, when I worked out the eigenvector originally over here, you'll notice the eigenvector that I wrote down was negative 1, 1. But then when I figured out what W2 was, I didn't get negative 1, 1, but what did I get? Negative 2, 2, which is just a multiple of an eigenvector. And so we're not surprised by that because a multiple of an eigenvector is just another eigenvector, right? It's in the same eigenspace. So this is a reasonable expectation. Now, sometimes I'll have students who will say, oh, well, I just want to change it to negative 1, 1. Because it's like, well, that was the eigenvector we got. So can I do that? The answer is no, you can't do that. You have to live with whatever W2 is based on this calculation. So it's nice to see that it's a multiple of the eigenvector, but we shouldn't just willy-nilly decide that we're going to change it to the original eigenvector. We should just keep whatever the calculation gives us here and kind of go with that. This making any sense? Are there questions on this? This was a 2x2 case. Yeah, Nathan, go ahead.
Will the eigenvector always be like the non-row version of it? So like, what, the only reason we got negative 1 was because.
I cut this in half.
So
yeah.
if we don't do that, would always.
No, it can be a little bit wild anyway, but it should be a multiple of the eigenvector that you got it. Yeah, it's not necessarily going to be possible to get it to match up for sure. Okay, guys, I want to talk about 3x3 versions of this. Let's talk about 3x3, and then we'll see how much time we have to do how many of the cases there are. 3x3s are harder. This 2x2 thing is pretty straightforward. The 3x3 case is a little harder. So what about by 3 defective cases? There's actually 3 different ways that a 3x3 matrix could be defective. Namely, so I'm gonna have 3 cases for you here, guys. And before you take Tuesday's midterm, you are going to want to make sure that you've practiced all 3 cases because they behave a little bit differently. I'm gonna have time probably to do at least 2 of them just in class right now. But here's what I'm talking about. In the first case, you might have, you know, a lambda 1, and then you might have a lambda 2 that repeated twice. And maybe the lambda 1 gives you the eigenvector v1, but then the lambda 2 only gives you 1 eigenvector. So this would be a defective scenario, right? This is a case where there's an eigenvalue that repeated, but it only gave you 1 eigenvector. Okay, so I like to refer to this. Well, sorry. So how are you going to get your 3 solutions here? If it's 3x3, we need 3 solutions, right? 3 linearly independent solutions. The first solution in this case would just be e to the lambda 1t times v1, right? No problem. You just write that down. And then, of course, the second solution, which is x2 of t, this would be e to the lambda 2t times v2. No problem. Okay, that's how we make these solutions. But then how do we get the third solution? Well, it turns out that for the third solution, you just do exactly what we did a few minutes ago. You just do the same thing again. You just write it as e to the lambda 2t times w1 plus t times w2. So that's all you have to do. So you just do, in other words, there's nothing new here. there's nothing new about this. This is the same sort of analysis that we just did in the 2x2 case, and that'll give you those solutions. This scenario, I like to refer to this case as the mixed eigenvalue case. This is the case where there's not just a single eigenvalue, but there's two different lambdas, one of which repeats and which doesn't pull its weight. That's defect. That's one way that you could have a defective system. Okay, I'm gonna need a little more room here, so I'm gonna put the third case somewhere else. The second case would be, what if I had the same lambda 3 times? Lambda, lambda, and lambda. And what if in this case, we only got 2 eigenvectors? So this would be an eigenvalue that's not pulling its weight because it has a weight of 3, but it's only giving me 2 eigenvectors. Question is, again, how do I come up with 3 solutions here? So the way we're going to do that, guys, is x1 of t, of course, e to the lambda t times v1. Okay. And then for the second solution, which is x2 of t, we're going to have e to the lambda t times v2. So we can start off with just the 2 standard solutions that comes from the 2 eigenvectors that we did get. And then the third solution, again, guys, nothing weird. We just have e to the lambda t times w1 plus t times w2. Same thing again. And again, how do you find w1 and w2? It's the same diagram that we already looked at for the 2x2 case. So we don't have to do anything new here. There's nothing clever or creative going on. We just choose w1 so that it won't survive the square of a minus lambda I, but it will survive a minus lambda I. That's the idea. This one, I generally will refer to this as the regular defective case. That's regular defective. Okay, so we have mixed eigenvalue, we have regular defective, and what's the third case going to be? I'm gonna put it over here, guys. How else could we have the matrix be defective? Jason?
3 repeated lambdas with 1.
Exactly right. 3 repeated lambdas, but only 1 eigenvector. This is what I'm going to call the super defective case. This eigenvalue is seriously failing to pull its weight, right? It has a weight of 3 and it's only giving me 1 eigenvector. All right, well, how am I going to get my 3 solutions in this case? Write them down again. x1 of t, as you would expect, it's just e to the lambda t times v. Nothing wrong with that. But I already, when I go to the x2, I already have to start doing this w stuff. So this is going to be e to the lambda t times w1 plus t times w2. Nothing surprising there. But now it's like, what do we do to get the third solution? We've already milked the trial solution we were using earlier. It turns out here we have to really dig deep to come up with a third solution. And I'm going to tell you what it is I'm not going to do the derivation like I did over there for the red part and the blue part for this one. I'm just going to tell you what it is, but it's the same idea. It's going to be e to the lambda t times, okay, you ready for this? W3 plus t times W4 plus, oh, here we go, t squared over 2 times W5. Again, somebody way smarter than me and way before I ever showed up figured out that this is the form of what we need to make for our third solution. And the $64,000 question now is, well, how do I get W3, W4, and W5? Well, guess what? There is going to be a picture just like this one. It's just a little bit bigger. It's just a little bit bigger. I'm going to draw the picture for you guys here. W3 has an arc. Remember, every time I multiply by A minus lambda I just think of that as an arc on my diagram. And W3 goes to W4. Then W4 goes to W5 by doing A minus lambda I again. And then W5 finally becomes 0 after we do A minus lambda I again. I love these diagrams, and I honestly think they should be in our book because it's a visual way to easily remember what to do. We're going to choose W3 right here. We're going to start by choosing W3. And what needs to be true here, guys? What needs to be true is that W3 has to survive 2 powers of A minus lambda I so that we can generate W4 and W5. But then W3 should not survive 3 powers of the matrix. Isn't that weird? So the powers are gonna get jacked up here. Let's write it down just so it's totally clear. I think I need to come over here to give myself just a little more room for this. So, I shouldn't be erasing this diagram yet. Yeah, so the point is we're going to choose W3 such that A minus lambda I cubed times W3 is 0. And if we only do A minus lambda I squared to W3, it should be not 0. Now, if you're really on the ball with this and you realize you're in a super defective case, and you're like, yeah, I'm going to have to do the W3, W4, W5 business. You know what you can actually do to save yourself a little bit of a headache? You can do the W3, 4, and 5 first, and then recognize that if I just kind of ignore the arc that's on the left, and I think of the W4 and the W5 as being in the positions where the W1 and the W2 were in the original diagram, you can actually do that. You can choose the W1 and W4 to be the same, and the W2 can be just the same as the W5. Okay. I think we need to do some examples. Surprisingly, I do not think that the super defective case is the hardest one. The reason I don't think it is that as it turns out, even for a 3 by 3 matrix, A minus lambda I cubed is going to just be the all 0 matrix, just like it was here. And that makes it easy. If this matrix is all 0, then this first condition becomes automatic. You don't even have to break a sweat to figure that out. And you just have to focus on the second condition. It's actually relatively easier. The hardest case of these 3, in my opinion, is the mixed eigenvalue case. Because in that case, the A minus lambda I, even squaring it, is not necessarily a matrix of all 0s. And so it's a little trickier to choose the W1 and the W2 here. That's really my point. Okay, so I think what I'd like to do is maybe we can do one case now and then we'll take a break. Does that sound good? The easiest case for sure is the regular defective. That's the easiest of these 3. So I think I'd rather focus on the ones that are maybe the harder cases first. Let me find a good one. Yeah, let's do one example before we take a 10-minute break today. Okay. So example. example, let's solve x prime equals a times x, where, now let's write down what A is. A is going to be the matrix. This is a 3 by 3. It's going to be a 6, 5, 1, and then 0, 5, 0, and then -1, 2, and 8. Okay, so this is the question. I think for the purposes of focusing on the material from this section, I'm not gonna drag you through finding the eigenvalues. You should definitely cofactor expand on the second row once you have a minus lambda I written down, because the second row has all the zeros in it. So be clear about that. I noticed on the extra credit quiz, there were a lot of people who were just, without even thinking about it, going straight to row 1. Right? It's not always row 1 that you want to expand on. Sometimes it's a column, sometimes it's a row. So really look at your matrix closely. Where are those zeros so that you can find the right row or column to expand along. But I'm going to just give as a hint here that the eigenvalues are 5, 7, and 7. Okay, so we won't write out the whole characteristic equation this time. I'm just going to give you these lambdas. Don't forget that we have fun facts that can be verified, right? The trace of this matrix, if I add the main diagonal, 6 plus 5 plus 8, that's 19. So my lambdas should add up to 19, right? And that's one thing that you can use to just confirm it. And yeah, so that's reasonable. So let's go ahead and start doing the solution here. Which eigenvalue would you normally maybe think about doing first? Pardon? Why would you do that one first? Actually, it doesn't really matter. Let me cut you off. So do we know if this matrix is defective yet?
No.
We don't know that because we don't know whether the repeated eigenvalue is going to pull its weight or not. So if you wanted to kind of know whether your matrix was defective or not, I might start with 7. But you are making a good point that it really doesn't matter because you do have to look at every eigenvalue here anyway. So I'm gonna go with your idea. So we're just gonna start with lambda equals 5 here. Okay, and so I'm gonna do a null space. I'm gonna go fairly quickly on this, guys, because honestly, 90% of this is chapter 7. We're just reviewing chapter 7 here. So I subtract 5 off of the main diagonal. So I get 1, 5, and 1, and then 0, 0, 0, and then -1, 2, and 3. So I've subtracted 5 off of the main diagonal. Remember that this matrix cannot be invertible, and we can easily see here that there's a row of 0. So I'll just cross that off. I'm going to go ahead and do an ERO. I'm going to add the first row. Well, first of all, I'm going to put the row of all zeros on the bottom, and I'm just going to add the first row to the bottom row. So 1 plus -1 is 0, 5 plus 2 is 7, and 1 plus 3 is 4. So there you go. You've got pivots sort of like this. And there's a free variable here. So this time I think I will just go ahead and set up a free variable for z. So z is going to be free. I'll call it t. And then I have to figure out what y is. I do know that 7y plus, let's write it down, 7y plus 4z should cancel out to 0. That's what the middle row of this row echelon form tells me. So if I solve this for y, it looks like y would be -4/7 of t. I think I did that right, hopefully. And then we have to figure out what x is by using the first equation. So x plus 5y plus z, that should be equal to 0. And now I'm going to use that to solve for x. So x would be -5y minus z. And so that's, what is that? -5 times y is like 27ths of t. And we subtract z, which is just t. And that becomes 13/7, I think, if I make a common denominator out of that. 13/7 times t. Sorry, I had to write that right on the bottom of the board here. 13/7 times t. Am I doing the math right this morning? I sure hope so. All right, so what's my eigenvector then? My eigenvector, after I bust out the t, I'll have 13/7, and then I'll have -4/7, and then I'll have a 1. Bust out the t, that's what I have. So z was equal to t, y was -4/7 of t, and x was 13/7 of t. So I've just busted the t out. Make sure you put x first, then y, and then z. Did I make a mistake?
Oh, no, just a question.
Yeah.
Other one with the 2x2, you can switch them as a negative sign. Do you have to do that for?
I did that little A-B trick on the 2x2. I can't do that so easily on a 3x3. I pretty much, so here I'm going back to the hard way of doing it, which is to set up free variables and kind of go through the motions. Okay, guys, so let's write down the first solution here, x1 of t. What's it gonna be? E to the 5t times this vector, 13/7, -4/7, and 1. Let's put a box around that guy. That's the first part. That gets us at least one solution out of 3 for our system that we needed to come up with. All right. So far, so question, Blake.
It's not to be nitpicky, but we can multiply that vector by 7.
Yes.
Fine.
Yes, if you don't like fractions, go ahead and throw a factor of 7 through that whole thing. Absolutely a good point. Yep. Scalar multiples of eigenvectors are always just as good as eigenvectors. Okay, let's look at our other eigenvalue, guys. Lambda equals 7. Okay, we'll do this, so we'll take a break after I get this done. Everything good back there? Okay, so I'm going to find the null space that corresponds to lambda equals 7. It's a 3x3 matrix again. This is subtracting 7 off of the main diagonal, -1, 5, 1, 0, -2, 0, and -1, 2, and 1. Okay, well, we have to be able to cross off a row. I'm just gonna go ahead and cross off the bottom row. And then I'm kind of looking at pivots that are like this. I'm thinking this is a defective matrix because I'm only gonna get one free variable here. So in fact, if I line up my columns with my unknowns, the second row here basically tells me that -2 times y is 0. And that tells me that y itself is already 0. So the y is 0. Yeah, Gilbert?
Why were you able to cross up the bottom when they were out with that?
I know that the matrix is not invertible. So I know that if I was going through the ERO process, I would get a row of zeros eventually. Now, I don't always know for sure which row it would be, but a good rule of thumb is that on a 3x3, as long as the other 2 rows that you did not cross off are not multiples of each other, then you made a good choice. So that's what we did here. We just got rid of the 3rd row. The first 2 rows are linearly independent, basically, so you can keep those 2 rows. Good question. Good question. Now let's figure out what the x and the z are from the first equation. So we have -x plus 5y plus z equals 0. But that's just from the first row of the matrix. But I already know that y is 0. And so now you can see that if we set z equal to, so z is really the free variable here. If z is equal to t, then you can see that x is equal to z as well. So x and z are both going to be equal to t. And so my x, y, z, right, is going to be t, 0, t. That's my solution. And so what's my vector here? My vector is going to be 1, 0, 1. If I bust out that t, I get 1, 0, 1. And so now I really do know that this matrix is defective. because the eigenvalue had a multiplicity of 2 and only gave me one eigenvector. Well, I can at least write down one solution here, which is e to the 7t times 1, 0, 1. That much I can do, and I'm going to go ahead and circle that as well. Okay, so we are 2/3 of the way done because I've found one solution right here for the eigenvalue lambda equals 5. And now for the eigenvalue lambda equals 7, I have found a second solution. So I've done this one and I've done this one because this is the mixed eigenvalue case, right? We have mixed two different lambdas here. I probably should have written that down. This is the mixed eigenvalue case right here. Okay. And so now the issue is, what about the third solution? So let's figure out what the third solution should be. Ooh, I don't want to erase too much. In this case, guys, we only need the W1 and the W2. Okay, that's all we need. Just redraw that diagram up here for ourselves so we can look at it again. W1, when I multiply by a minus lambda I, should bring me to W2, which when I multiply by a minus lambda I again, is supposed to bring me to 0. That's the diagram that is worth $1 million right now to understanding how to do this section. Okay, and we are going to choose W1. And again, how do we choose it? We have to choose, there's many right answers, but we have to choose it so that it will survive a minus lambda I, but not survive the square of a minus lambda I. Am I doing okay?
Yeah, I'm sorry, it's the first.
Yes,
Okay.
we're in case 1 right
Sorry.
here. Mixed eigenvalue. I'm gonna do, after we take a break, I'll probably do a super defective one, but let's start with just this mixed eigenvalue situation. So in order to not freak out at this point, guys, what you want to do is just calculate the necessary powers of a minus lambda I. So in this case, lambda was 7, and I need to just work out what is a minus 7i. Okay? Now again, that's actually this matrix, but it's this matrix without EROs done to it. So if you need to, just go back to A and subtract 7 off of the main diagonal. That should give you -1, 5, and 1, 0, -2, and 0, and -1, 2, and 1. That's a minus 7i. Okay? But we also need the square of that matrix because we have to make sure that W1, I lost my square here, didn't I? We have to make sure that W1 will not survive the square of this matrix. So a minus 7i squared. If I wanted to write that down, that should be this matrix copied down twice. So I write it down twice here, my friends. And then I have to multiply this out. Okay, so there's a little bit of everything on these kind of problems. We have to actually remember how to do matrix multiplication as well, which is where we take dot products of the rows of the first matrix with the columns of the second matrix. Okay, so if I go across, if I want to get the 1, 1 entry, I'm just going to dot row 1 with column 1 here. That's a 1 plus a 0 plus a -1. That's 0. Okay. What about the top middle entry? That's -5 minus 10 plus 2. That would be -13. What about the top right entry? -1 plus 0 plus 1. That's just 0. Okay. And I keep going like that. The left middle entry, I go to row 2 now and I dot it with the first column. I get 0 plus 0 plus 0. That is just 0. And then when I go to the middle entry, I have 0 plus 4 plus 0. That would be 4. Gives me 4. And then the right middle entry, that's 0 plus 0 plus 0 again, just 0. And finally, I have to go to the bottom row. I have 1 plus 0 minus 1, that's 0. And then -5 minus 4 plus 2, I believe that's -7. And then finally, I have -1 plus 0 plus 1, which is 0. And now we are coming to the reason why I think this is the hardest case. Is because if this was the super defective case, this matrix would have been all zeros, which would have made our lives easier because then pretty much anything would have been okay to choose for W1, or well, it would have been W3. I need to choose a W1 now, guys, that will survive this matrix, but not this matrix. So it's a sort of a little bit of a two-case thing we have to consider carefully. There's lots of right answers. Can somebody think of a vector, a column, and it doesn't have to be anything hard. It's not going to be anything hard. I just want to know, is there a column that I could set next to this matrix and it would not become 0, 0, 0, but if I set it next to this matrix, it does become 0, 0, 0. Eduardo? Would 1, 0, 1 work? Well, we're going to find out. If we set that there, then let's see what would W2 be. So W2 would be, well, where's my diagram? Right here. W2 would be A minus lambda I times W1. So here's A minus lambda I. Let's put 1, 0, 1 right next to that. Calculate it out. What do we get? -1 plus 0 plus 1. Uh-oh, that's 0. 0 plus 0 plus 0, that's 0. -1 plus 0 plus 1, that's 0. So this is not what we wanted, right? We need W2 to survive this matrix. Let me give you another reason why I knew that wasn't going to work. Because 1, 0, 1 actually happens to be exactly what the eigenvector V was over here. And if it was the eigenvector, what happens when you do this arc to an eigenvector? It becomes 0, always, right? So we need to change this a little bit. I'd like to tweak just one of the numbers only. Yes, Jason.
Make one of them.
Okay, so we could do 1, 0, -1. You want to try that? Well, let's try that. Got nothing to lose, right? Let's try again, guys. Sorry, I'm erasing a little bit. So let's try to choose W1 to be 1, 0, -1. So if I put 1, 0, -1 right here, then at least we're not using an eigenvector, so there's a better chance that this is going to be good. We have -1 plus nothing plus -1. Oh, good, that's -2. Okay, and then we have 0 plus 0 plus 0, which is 0. And then I have -1 plus 0 plus -1, which is -2. Guys, that is perfectly fine. W2 would then be -2, 0, -2. However, I'm not ready to declare victory yet. Because I need to make sure that this W1 that we chose does not survive this matrix, right? Because if I do 2 arcs, which means I'm squaring A minus lambda I, that W1 needs to become 0. Let's check it out. Put the 1, 0, -1 next to this guy. Now let's multiply this out. 0 plus 0 plus 0, yay. 0 plus 0 plus 0, yay. 0 plus 0 plus 0, yay. It all works. So W1 has been killed by 2 powers of the matrix, but not by 1 power of the matrix. Yeah.
I'm kind of confused. Could we just, for the second part, like multiply what we got for W2 by just 1 A minus I?
Okay, so Audrey's bringing up a good point. Once we found W2, we could have just gone back to the original matrix and taken this A minus 7I times this thing here. That would have been totally the same. That would be saying, I want to start here and just do 1 power of A minus lambda I, which would be this one, right? This power here. I think it's easier, though, to go back to the whatever your W1 was and So start here and imagine doing 2 powers of a minus lambda I to it and see if I get 0.
Is it easier?
Just because this vector is nicer than this one generally. And also this matrix has a lot more zeros in it than this one did. And so the calculation is just easier. It's not really conceptually easier, but it's just, I think it's a little nicer. Yeah. Okay, so guys, let's write down the second solution now. X2 of t is this is x3 of t. Sorry, this should be x3 of t. We already have x2 of t. So x3 of t is e to the 7t times w1, which is 1, 0, -1, plus t times w2, which is -2, 0, and -2. There you have it. I'm going to put a box around that as well. Clear enough? And guys, I now have x1, x2, and x3. I can write down my final answer. The final answer, I'm going to put it way up here, guys. X of t is c1 times x1 of t plus c2 times x2 of t plus c3 times x3 of t. And I don't mind if you just write that, as long as I can find your x1, your x2, and your x3. You don't need to recopy every time what you have. Okay, so you don't need to like write out this whole thing again, and this whole thing again, and this whole thing again. You can just write this as your answer. I will accept that. Sarah?
Do you technically need to calculate a minus 7i squared?
You do. You do, because you have to make sure that W1 will not survive it. And if I don't, in other words, if I do 2 powers of a minus 7i to W1, I have to get 0. And I won't know that, I won't be convinced of that unless I've actually calculated it. That actually makes sure that when I do a minus 7i squared, apply it to W1, that I get 0. We do actually want to calculate that.
Well, I meant like, because like you said earlier, you could technically times W2 to the original.
Mm-hmm. You are right, but I guarantee you, you will not do less work.
Oh, probably.
It
not
will be
this-
harder work than just, I prefer to just calculate all the powers that I need up front. The amount of work I will have to do that will never be more than somebody who is going to just try to live only with this matrix and keep multiplying things just by this matrix. So yeah, it is easier to do it, I think, the way that I'm showing it here. By the way, just as a little confirmation, the W2, everybody notice it's a multiple of the eigenvector that we originally had obtained. That's reassuring. I would expect that to be true. Yeah, Blake?
So when we get this problem like on the exam, basically just gonna put the thing.
For the choosing the W1?
Yeah.
You know, most choices will work. In fact, I was surprised nobody said 1, 0, 0. But 1, 0, 0 would have worked and would have made the calculation a little bit easier. So it is a little bit of trial and error to come up with that. That is absolutely true. Other questions here? Okay, let's take a 10-minute break. That's the mixed eigenvalue piece. When we come back in the break, I think I'll show you the super defective example, and then I think we'll be in pretty good shape on this. So we'll take a 10-minute break. Good about it? So again, the big picture of the summary of what we're talking about are the 3 cases that are on the board over here. I just did an example of a defective linear system, which is of the type mixed eigenvalue, okay? Which in my opinion is actually one of the harder ones. Super defective is notationally a little messier, but I actually think that it goes a little more smoothly. I'll let you be the judge of that. We're going to try an example of it right now to kind of wrap up our class day. This won't take us too long to go through. I put the question over here on the board that I'd like to work on with you. So let's find the general solution to this linear system that I've written down here for you. So what do we have? We have the derivative of x1 is equal to negative x1 plus x2. The derivative of x2 is equal to negative 2x1 minus 3x2 plus x3. And the derivative of x3 is equal to x1 plus x2 minus 2x3. So you notice I didn't actually give it to you as a matrix in this case, like I did on the previous examples. You should be able to take this and write it into a matrix form, right? This is, after all, just x prime equals ax. And what is the matrix A? You literally don't overthink this one. All you're doing to write down the matrix A is grabbing the coefficients from these equations. You're not doing any fancy footwork with them. You're just literally writing down all the constants that you see in front of all of these unknowns, row by row by row. So you just put those numbers in there, okay? So that's my matrix, and I'm going to give you a hint again, like I did on the previous example, of what the lambdas are. And by the way, I might do that on the test too, because you can imagine if you have the lambdas wrong, this is really not fun. You really have to have the lambdas correct. So the lambdas are, actually, I tell you what I would be like. Here's what I would do on the exam. I would probably tell you 2 of the lambdas and ask you to tell me what the third, ask you to figure it out from there. How would you figure out the third lambda if I gave you only 2 out of the 3? Using the trace, right? What is the trace of this matrix? The main diagonal? Negative 6, right? So if one of the lambdas is -2 and the second lambda is -2, then you can figure out from that that the third lambda is also -2. So I can play games like that. With those fun facts on the eigenvalues, I can give you partial hint, and then hopefully you guys will know those kind of facts that can help you find the other eigenvalues. So here you have it. These are the lambdas. And we only have 1, and it's repeated 3 times. Now, as of now, we don't know that this is super defective. In fact, this might not even be defective at all, for all we know. We don't really know yet. We have to go a little bit more into it. So I'm going to take a look at this eigenvalue, lambda equals -2. As always, we have to go find the corresponding eigenvectors by using this null space calculation. So how does that work again? Well, this is going to be A minus lambda I. That means I'm going to I'm going to subtract lambda off of the main diagonal, which really just means I'm going to add 2 to the main diagonal. So I'll have 1, 1, and 0, and then -2, -1, and 1, and then 1, and 1, and 0. Okay? And you can see that the first row and the third row are the same, so I'll just cross one of those off. And then I'm probably going to need to do an ERO real quick, so let's just do 1, 1, 0 here, and I'm going to take 2 times the first row and add it to the second row, so that's A1, 2 of 2. 2 times the first row added to the second row gives me 0, 1, and 1. Okay, so there's my pivot, and my pivot. And I see that I only have 1 free variable. So if I think about X, Y, and Z here, like we usually do, setting it up the same as always, right? Z is going to be the free variable here. So I'll write that down, Z equals T. That's the third column, no pivot, right? And then from the middle row, I see that Y plus Z should add up to 0. So that means that Y has to cancel out the Z. So the Y would be equal to -T. And then if I go back to the first row, I see that X plus Y should cancel out. So X plus Y should be 0, so that X is actually equal to T as well. And there's your XYZ solution. I'm going to bust out my variable, like always, and get my eigenvector. So if I bust out the T, it looks like I'm just going to end up with 1, -1, and 1. Okay, now I'm pretty sure that this is super defective. The eigenvalue shows up 3 times here and only gave me 1 eigenvector. So we can build one solution without too much of a sweat, right? x1 of t, this will be e to the -2t times the vector 1, -1, 1. I can go ahead and at least get that down on paper first. And remember, guys, if you see a problem like this, it's a pretty substantial amount of work. If you don't think you can do the whole thing, do whatever part of it you can, because I want to give you guys as much points as possible. So if you just do this much, you haven't even really gone into the defective piece of it yet, but I can give you something for sort of knowing how to at least get started on it. So do as much as you can on these problems. But at this point, we really are in this super defective case. I've got my diagram over here. And what I'm going to do is try to figure out something about what W3 needs to be. In order to do that, you can see that I need powers of A minus lambda I. So let's just get some powers of A minus lambda I written down. So the original A minus lambda I would be this, right? A plus 2I. And that's just the original matrix. And again, I just want to reemphasize, I mentioned this earlier, but I want to say it again one more time, loud and clear for everybody, that you must use the matrix A minus lambda I without any EROs done to it. So you cannot use this matrix. Right? You have to go back to whatever A minus lambda I was, which was what we originally wrote down here. Okay? Now, I need to square this. Okay, so I'm going to go ahead. I had some people objecting earlier. They wanted me to just keep using this matrix to do everything. I could, but I promise you it'll be nicer and more organized for you if you actually just go ahead and bite the bullet here and work out these calculations. So I'm going to go ahead and do that. I'm going to take this matrix times itself. Okay, so if anybody has sort of gotten a little rusty on matrix multiplication, I mean, we did learn it after all back in chapter 2, which was back in September during our heat wave, a long time ago. So I had to remember, how do we do this? If you need to review this, be sure to do it, because yeah, we absolutely have to be able to do this. Let's start multiplying this out. So 1 minus 2 plus 0, that's -1. And then 1 plus -1 plus 0 is 0. And then 0 plus 1 plus 0 is 1. And I'm just doing dot products. I'm doing them pretty quickly because this is, you know, old material, but I'm just telling you exactly what I'm doing. For the second row, I go across the second row of this matrix and I dot it with each of these columns. -2 plus 2 plus 1. That's 1. And then the middle entry is -2 plus 1 plus 1. That cancels out to 0. And then the third entry is 0 plus -1 plus 0. That's going to be -1. Okay? And then we get to the bottom row of the matrix and we do the same thing one more time. We take the bottom row and dot it with each of these columns. 1 minus 2 plus 0, that's -1. And then 1 minus 1 plus 0, that's 0. And then 0 plus 1 plus 0 is 1. So there you go. That is A minus lambda I squared. And because we are in the super defective case, I should have written that down, by the way, somewhere. Super defective. Because we are in the super defective case, we technically have to have 3 arcs of A minus lambda I. That would mean we need to cube this matrix. Well, the best way to do that is to just take what we already have, which is the square of the matrix. Let's just put that here. The square of the matrix is here. And just multiply it by the original A plus 2I one more time. So I'm going to copy it down again here. Like so. So this is literally just to get the cube of the matrix, but I am going to go fast on this and not even do the work. I'm going to tell you what you're going to get, and I'm going to... Yes.
Isn't there one in the third column?
Nope, there sure is. I'm going too fast. That's the trouble. Yeah, there we go. Thank you. Does that look good to everybody? So this is A minus lambda I squared, and this is another A minus lambda I. So altogether, that would be 3 powers of this thing. What you will get, if you do actually carefully go through the dot products, is all zeros. And now here is the nice thing about the super defective case. This will always happen for a 3x3. For a 3x3 on the super defective case, you're not going to have to sweat it too much this will always happen. Which means that no matter what you choose for W3, by the time you hit it with 3 powers of A minus lambda I, it will be 0. You don't have to worry about that. It will definitely be 0. So the key thing we need to do is choose W3. By the way, you might be wondering what's going on with W1 and W2. I'm going to come back to W1 and W2 in just a minute, okay? But I want to get this W3 thing figured out first. I need to choose a W3 that will survive this matrix, and actually it should even survive this matrix. I just don't want it to survive this matrix. But it's not going to survive this matrix. I'm good to go with that. So I just need something that I can put right here that when I do the matrix calculation won't give me 0, 0, 0. Does anybody have a proposal for me? Lots of right answers. Jason?
1, 0, 0.
Let's make it easy, guys. Don't pick big, messy numbers. Pick something like 1, 0, 0. The reason that is nice. Now, I'm not saying this will always work, of course. Actually, let me give you an example of something that would not have worked. It would not have, you don't need to write this down, just gonna watch for a second. If I had chosen 0, 1, 0, this would not have worked, because if I put 0, 1, 0 right here, what happens is this calculation picks off the middle column of this matrix, and that's bad. That vector would have been killed too soon. It would not have survived that power. So you can't just be totally blindly doing this, but 1, 0, 0 in this case is going to be a really good choice. Let me rewrite this. Now you can take the notes again with the correct vector here. Does everybody understand that, when you use, so if I have some random matrix here, I think I probably made this point 10 weeks ago. If I take a random matrix like this and I hit it with 1, 0, 0, you know what happens? You just get the first column. You just start doing these dot products, you realize you just get ADG. Right? That's the beauty of 1, 0, 0 or 0, 1, 0 or 0, 0, 1. You just pick off columns of the original matrix. So if I choose 1, 0, 0 here for W3, then I can easily write down what W4 is, because W4, I obtain that by putting 1, 0, 0 right here. And when I do that, I'm going to get the first column of this matrix. So W4 is 1, -2, and 1. Again, how do I get W4? I start with W3, which I chose, and I hit it with A minus lambda I. I just do this calculation. And because because Jason chose such a nice vector here, 1, 0, 0, this calculation is literally something you can just glance at. You're just picking off the first column of the matrix there. Okay, so now what about W5? I'm going to ask Audrey. To do W5, you have 2 choices. You can either take W4 and put it right here next to the original. You can either put W4 right here, which would mean that you're standing on W4 and you're going to multiply 1 power of A minus lambda I that moves you over to W5. Or you can go back to W3 and put it next to the square of the matrix. My question is, to get W5, would you rather stand on W4 and multiply 1 power of A minus lambda I? Or would you rather go back to W3 and calculate 2 powers of A minus lambda I to directly push you to W5? Anybody have a preference? Alex?
I mean, in this case, it's easier to go from W3 because the matrix is easier, the vector is easier.
That is not just in this case, that is like always true. Absolutely right. I think it's not wrong. It's not wrong to do this one, but it's easier to do this one because I have 1, 0, 0. This is my A minus lambda I squared, and I know that I'm going to pick off the first column of that matrix. So that's my W5, -1, 1, and -1. Isn't that beautiful? That's W5. So that's the idea. It's just so much nicer to go back to W3 rather than to use W4. Now, the other point that I had made a moment ago, guys, a little bit ago, is that this W4, if I just ignore the arc on the left, if I want to know how to get a good choice of W1 and W2, I can actually just kind of look at this much of the picture. And where I have W4, that's the place where the W1 was in the original diagram. And the W5 is sitting in the position where the W2 was before. So we can literally, you don't have to do this, but it's going to make your life easier to just go ahead and align W1 with W4 and W2 with W5. So, and by the way, where are the W1 through W5? They're parts of these second and third solutions that we're about to write down. Let's write them down. I've got x1 of t here. So what's x2 of t? x2 of t, this will be e to the -2t times W1. I'm going to steal W4 and use it as W1 as well. Plus t times W2, but I'm going to steal W5 to use that as W2. So there is your x2 of t. Okay, put a box around that one. That's x2 of t right there. And then I'm going to go ahead and write down x3 of t. Okay, we're pretty much ready to just go straight into it. X3 of t, that's e to the -2t times. So now we just have to remember this formula. W3, you might want a flashcard or two for the x1, x2, and x3 in this case. But we start with W3, which was 1, 0, 0, right? Plus t times W4. W4 was 1, -2, and 1. And then plus, here's the weird part, we have to do t squared over 2 times W5, which was -1, 1, and -1. So there you go. This then, I'll put that in a box also. That would be your third solution. That would be your x3. Notice how the W1 and W2 is just shifting to the positions of W4 and W5. Okay, it's not so terrible. And so then finally, the final answer, you know what the final answer is? Right here. Same thing as we had before, just C1 times X1 plus C2 times X2 plus C3 times X3. That's all we have to say. Yeah. We getting this a little bit? It's actually not that bad. It's not that bad. I really recommend just crank out these powers first before you start getting lost in which W goes where and where am I in the process. Just get all these powers written down first. Then it becomes super easy to go through this piece of the process. By the way, did you all notice the W5, which is also the W2, is a multiple of the eigenvector again? We've seen that a few times today already. That's always going to happen. That last W, that last surviving W before you hit 0 is always an eigenvector. It may not be the same eigenvector that we had from before, but it's always an eigenvector. Oh my gosh, I'm out of time. I could talk for 2 hours about this. I love it so much. Any questions here, guys? Before you ask your question, Marco, unless everybody needs to hear it, I want to pass out these group works. Guys, on your way out, just grab one of each of these group works, okay? And we'll do this during the review session this weekend, or you can just do it on your own. So come grab group work 14 and 15, one of each of those on your way out the door today. The solutions are in Canvas for that, but those are some good practice problems. Okay, Marco, did you have a question?
And should we be expecting imaginary numbers?